Hi, come on in. Up there, there's more room on this side. Yeah, notes at the end there.
Is this the only one there was? Yeah.
For me, yeah,
Okay.
yeah.
Cheers.
All right then, good afternoon, everyone. So it's the second lecture from me in the Maths Fundamentals. You'll be having another lecture, is it immediately after this? Or shortly after it with Saeed, so he'll begin his half of the unit. But for now, so I'll continue on where we left off last time. So if you weren't here last time, the summary, the crucial information is in the notes, and you can access the recording of the lecture online. I'll show you that at the end of today. But without further ado, I guess we'll pick up and continue on. So we introduced last time the idea of convergence and divergence. First of all, very briefly, as convergence and divergence, well, convergence is the idea of some extended process getting closer and closer to some final limiting state. And we pointed out areas in applied mathematics and pure mathematics where this is a very important fundamental idea. Let me specialize it a bit to that, us beginning to look at convergence, we're going to look at sequences and series. Okay, so we defined a sequence. A sequence pretty much matches the common sense notion of a sequence. Sequence is one thing after another. So for us, a sequence of numbers is just going to be an extended list of numbers. First element, second element, and so on. Okay, so we have this notation shown on the screen there. We can talk of, without being specific, we can talk about a sequence of values x. X1 is the first value, x2 is the second value, x3, and so on. So you got this subscript, you got this index in the subscript. And typically, we'll be talking about sequences that can be extended indefinitely, so-called infinite sequences. There's no end to them. We looked at a bunch of examples. I won't go back over those again. And then I think we finished last time by considering a certain family of sequences, two important families, the arithmetic sequences and the geometric sequences. Okay, and we talked a little bit about that, and I think this is picking up where we left off last time. So, I mean, this shows you a nice example of a geometric sequence. For instance, a sequence of values 1, a half, a quarter, an eighth, and so on. Those are all the increasing powers of a half. Okay, a half to the power 0 is 1, half to the power 1 is a half squared is a quarter, half cubed is an eighth, and so on. Okay, so that's a nice geometric sequence. It's got some initial value, which is 1, and each subsequent value is this fixed multiple, namely a half times the previous value. So we can give a nice compact formula there for the sequence. We can say it's a sequence of values a, and the an, the nth element, is a half to the power n minus 1. So the first element is a1, and that's a half to the power 0, which gives you your 1, that initial term of 1 there. Okay, we'll meet the idea of geometric sequences and the associated geometric series. We'll meet those as we go through the course. Of course, one area in which they crop up, very importantly, is in compound interest, for instance. So if you take out a loan, a simple loan, or do a simple investment, like depositing a certain amount of money into a bank account, so this is phrased as putting an amount into a bank. So if you put P units or P pounds into a bank, and if there's an interest rate of R% per year, say, then the value of the bank account, if you don't put anything else into it or take anything else out, just due to the accrual of the interest, according to compound interest, where you get paid the interest at the end of every year, so that increases the deposit slightly, and then you get interest on all of that over the second year and so on. So you get this formula here. You might recognize this is the future value at year n of the initial investment P. And you can see it takes the form of a geometric sequence. Our general form for geometric sequence when we introduced it was that an, the nth element, had this form a, some initial value a, times r to the power n minus 1. And this is fitting that this is fitting that pattern here as well. So the initial value p times the fixed multiple to the power n. I've got the power n there. What about the power n? Oops. Yeah, this particular sequence is good. The index is going to start at 0. So year 0 is just the moment the money is placed in the account initially. So when n is 0, the 1 plus r percent to the power 0 is just 1, so it's just p. So v0, the initial amount, is just p, and v1 will be the amount at the end of year 1, and so on. So just the indexing is slightly different to the other one. And finally, maybe just end by looking at a sequence which is neither arithmetic nor geometric. I mean, not everything is so well behaved. You know, if all sequences were either arithmetic or geometric, we should probably all go home now because there's nothing much. You know, they're extremely simple to analyze because they're so regular. But plenty of sequences are neither. So, for instance, this one would be quite natural to look at: 1 over n squared. That's 1, a quarter, a ninth, and so on. 1 over n squared. That's neither arithmetic nor geometric. Doesn't fit the pattern of either. Okay. So it's a negative example. Okay, so we're going to get a bit more active in a moment. We'll do some work on the page. So we want to work towards the idea of convergence. So convergence we can think of as the long-term behavior of a sequence. What the sequence is doing, you know, all the way out along the sequence, at infinity, if you like. Well, before we get to that, or just as a stepping stone to that, we'll just deal with not the convergent behavior, but maybe the increasing or decreasing behavior of the sequence. And again, it's introducing some more terminology as well. So such sequences are called monotonic. So a sequence is monotonic if it's increasing, or, on the other hand, it might be a decreasing sequence. Okay? And it pretty much is, as what it sounds like, an increasing sequence of values x is one that satisfies the top inequality. So x1 is less than or equal to x2, which in turn is less than or equal to x3, and so on. Okay? So the terms in the sequence are getting bigger each time. Similarly, we can have a decreasing sequence where the inequalities go the other way. So x1 is bigger than x2, x2 is bigger than x3, and so on. Okay, the inequalities given there are what we call the weak inequalities, so it's less than or equal to. But you can also talk about strictly monotonic, or strictly increasing, or strictly decreasing, if instead of those weak inequalities, we replace them with the strong version. So x1 strictly less than x2, x2 strictly less than x3, and so on. That would be a strictly increasing sequence. So we're going to look at a few problems now. And the problem we're going to look at is, given the formula for a sequence, can we prove, or can we give a good mathematical argument for the fact that it's an increasing sequence, or maybe it's a decreasing sequence? And there's at least two approaches you could take to this. The first approach is to examine the difference between successive terms. So by successive terms, in the sequence, I mean one term in the sequence and the one that comes after it, okay, or before it, whatever. So we look at this difference here, where you could think of an plus 1 minus an. So an plus 1, where the index is the value n plus 1, that's somewhere out along the sequence. Depends on the value of n, of course. But an is the sequence element that came right before it. So when you look at that difference there, depending on whether that difference is positive or negative, that's going to tell you what the relationship between those two numbers is, which one is bigger and which one is smaller. So if we can establish one of these inequalities, that an plus 1 minus an is always bigger than 0, or that it's always less than 0, if we can establish those for all values of n, then we'll be able to conclude that the sequence is either an increasing or decreasing one. So for instance, if it's on the left, if an plus 1 minus an is bigger than 0, just rearranging the inequality, that means that an plus 1 is bigger than an, so that's an increase in sequences. Yeah? Because the n plus 1th element is bigger than the one that came before it. And the other one would be decreasing. That's one way of doing it, or an alternative way. It's actually an equivalent way, but it's just a different way of approaching it, and it works better for certain formulae, or it's maybe a little bit easier to carry out, is that to look at the quotient between successive terms, the fraction between successive terms. So you could take a term an plus 1 and divide it by the previous term an. Of course, now you're not comparing it to 0 now. You're not interested whether this is positive or negative. Now you're interested how this compares to 1, whether it's bigger than or less than 1, because that tells you which part of the fraction is the bigger one. Fraction is less than 1, or is absolute value less than 1, tells you the bottom is bigger than the top, and vice versa for a decrease. Okay. So let's dive in and have a look at this example, which is example 1.6. So here we're considering this sequence. So we'll take it to be the infinite sequence beginning at 1 and going up to infinity, where the element an is defined by this formula, 5 to the power n divided by n factorial. So n exclamation mark is n factorial, remind you. So the factorial of an integer, the factorial of a positive integer, you can see in the slide there, it's the product of that integer n and all the integers less than, all the way down to 1. So n times n minus 1 times n minus 2, etc., all the way down to 1. Okay, so let's use the ratio approach for this. So we'll examine an plus 1 divided by an. And we'll compare this to 1. So we'll examine this fraction, see if we can simplify it a bit, see if we can get a clearer picture of what it is, and make a comparison of it to 1 to see whether it's bigger than or less than 1. Well, we'll think of an plus 1. So an plus 1, so you have to take this formula here and write it out with n replaced by n plus 1. So this will be this quantity here, 5 to the power n plus 1 divided by n plus 1 factorial. And to divide it by an is the same as multiplying it by the reciprocal of an. So when you take an and you turn it upside down. Remember, what is n? N is the value of the index, which tells you which position in the sequence you're looking at. So n is some number 1 or larger, some integer 1 or larger. Okay, so we got two fractions multiplied together, but we could certainly simplify them down a bit, okay? Because there's a load of 5s on the top and there's a load of 5s on the bottom. Most of them will cancel off with each other, yeah? So we'll just be left with 1 5 on the top. So there's n plus 1 factors of 5 on the top and n on the bottom. So that's going to simplify down to leave you with the 5. And the factorials simplify as well, because this factorial is more or less the same as this one, because this is n times n minus 1 times n minus 2, etc., all the way down to 1. This one is pretty similar. It's n plus 1 times n minus 1 times n minus 2, etc. So the factors in this factorial, sorry, the factors in the top factorial are all present in the bottom. So you can cancel off all those factors. So you'll just be left with n plus 1 down here. And, well, we can't really simplify it anymore. It's 5 divided by n plus 1, and n is just a general positive integer. But we can make a comparison to 1. So how does this compare to 1? Is it bigger than or less than 1? is it bigger than or less than 1?
Depends on it.
Depends what n is. So describe the possibilities.
N is less than 4, it'll be
Yeah.
4. It's less than 4.
Yeah, so when n is 4, when n is 1, 2, 3, it's going to be 5 divided by something small, so it's going to be larger than 1. Then when n is equal to 4, it's equal to 1, so it's 5 over 5. But every value thereafter, for all the values of n strictly bigger than 4, it's going to be 5 divided by something larger, so it's going to be less than. So for n between 1 and 4, we have an plus 1 over an is going to be greater than or equal to 1. But for all n strictly bigger than 4, we get an plus 1 over an is strictly less than 1. You give some, if you can, give some nice complete description of the situation. That's all the relevant values of n dealt with, because n is some positive integer, 1 or larger. So that describes them all. So apart from these few initial terms where the sequence is going to be increasing, really it's a decreasing sequence. So you can say for all n strictly bigger than 4, see this inequality, you can rewrite that as an plus 1 is strictly less than a. I.e., it's a decreasing sequence from n equals 5 on. Is that okay? Any queries about that, or any clarification anyone would like on any of those steps there? So it's an example of a little proof dealing with this specific sequence. Remember, I'll scan in all these pages and make them available afterwards, but it's still a good idea to take your own notes and to develop these in the class as well. So is that okay? Any clarification I could give on that? Yes.
So is it increasing?
Well, it's increasing for a little bit at the beginning, first few terms, but then from then onwards, it's decreasing. So yeah, so you have to be careful. You shouldn't describe the whole sequence as decreasing. It goes up for a little bit, but after that, then for the rest of its life, it's a decrease. Yeah. So just give that qualification about the beginning of it. Yeah.
I'm confused.
Yeah. Go on.
Because
It's entirely possible I've made an error as well. So go on.
because 5 over 1 is bigger than 5 over 3, for example.
Sorry, have I messed up here? Hang on.
So isn't it still decreasing when it is 3 and 4?
Yeah, that fractional quantity does.
Oh, okay.
But that fractional quantity isn't the sequence element. Yeah, that's okay. So that's the ratio between them. Yeah. So the ratio, yeah. So you're right. You're observing that the ratio is always decreasing. But it's not. But what's relevant here is whether the ratio is bigger than or less than 1. That tells us what the individual parts of the ratio are doing.
Okay.
No, but that's a very good question because that teases out, the different aspects you're seeing. But that's what you should all be trying to do because you get great kudos for spotting my mistakes on the board. So hard luck this time, but someone's sure to be successful soon. So. So let's look at another one. Well, there's a bunch of them here we can have a little practice with. So yeah, let's talk through the SN one together. How are we doing for time? So these examples aren't in the notes, these are just some extra ones. So we'll consider the sequence Sn, where Sn is defined as 3n over 4n plus 1. Of course, what I'm not doing here is actually looking at I'm not doing any calculating here and actually looking at what the actual values of the sequence are. Of course, that would be a thing to do as well. And that certainly is a good thing to do, and that will tell you, or you will show you how that part of the sequence is behaving. But of course, it does only show you what part of the sequence looks like. What we're trying to emphasize here is how we can get these general arguments that apply to the whole of the sequence. So the conclusions I got on the previous page, or the descriptions I gave, were referring to the whole of the sequence, not just looking at some specific values at the front of the sequence. Although that of course still is a good thing to do. Well, I mean we could do that quickly for this one. Let's just see what the answer should be before we do it. So I'll just show you a little. This is just an online computation thing that comes up quickly. This is the mathematical system SAGE. I'll show you some more stuff with it as we go through the course, but I'll just do a quick, probably can't see that very well. So what is this? 3 times n over 4n plus 1. So it's that for n in range 100. So it should show us a little graph. Yes, that's pretty clear. What's that sequence doing? Is it increasing or decreasing? It's increasing. Starts down low, or there somewhere 0.6 or whatever, and increases. Is it converging or diverging? To some value slightly bigger than 0.7. Yeah, so it is converging. So the x-axis is just the position in the sequence, and then the vertical axis is the value. And anybody say what it's converging to? 3/4, yeah. I mean, the sequence is nearly this, 3n over 4n. And then you can cancel the n's, and so the thing is 3/4. But of course, it's not exactly, this 1 is added to the denominator. So that increases it, so it makes it slightly less than 3/4. But of course, as n gets larger and larger, by the time you're out to n equals 80 or n equals 100, the fact that you're adding 1 to it is really, it's becoming less and less significant, isn't it? So at an approximation, this is behaving like 3/4. And it's getting closer and closer to 3/4 as n increases. Now, so that's a good observation to make, but we'll be developing a very rigorous description of exactly what convergence is and exactly how we can prove that things converge to certain values, in a few lectures' time. So let's come back to this example. So, okay, so we expect to see increasing behavior. Well, let's see if we can prove it, because the devil's advocate could say, well, okay, although the graph looked like it was increasing, but, maybe when you get out to n equals 1 million, it does a funny, it decreases for a bit or something. Who's to say? So can we come up with a really strong argument that will say that this is always increasing? So we'll consider the difference approach this time. Just to see the other approach in action. So we'll look at Sn plus 1 minus Sn. Look at the difference between consecutive terms in the sequence. Now just be careful when you're putting down these things. Make sure you interpret the n+1th element correctly given the formula for Sn. So you have to replace n with n+1. For n+1. Okay, so we've got two fractions there. We're subtracting them. It's not immediately obvious whether this is, remember, we're doing the difference approach, so we should be comparing this to 0. We want to find out whether this quantity, whether this difference is bigger than or less than 0, positive or negative. Okay, looking at the fractions on the right-hand side that I've brought it to, it's not immediately obvious which this is. Is it bigger than 0 or less than 0? But it'll be a lot easier to decide whether it's bigger than or less than 0, I think, if we bring it to a single fraction. Well, let's just, so this is 3n plus 3, 4n plus 5 minus 3n over 4n plus 1. So let's bring it to a single fraction. So we're looking over the common denominator of the product of the two denominators. And then you're going to have 3n plus 3 times 4n plus 1 minus 3n times 4n plus 5. Is this bigger than or less than 0? It's maybe a bit hard to tell. Maybe we should simplify the top a bit. So let's make sure. So you get 12n squared, but then you also subtract 12n squared there, so that's going to cancel out. So there's no n squareds. How many n's? There's 3n and 7n there, so there's 10n in the first product, and there's minus 15n, so 10n minus, that's going to be minus 5n, isn't it? Plus 3. It's highly likely I made a mistake there doing all that, but maybe not. The 12n squared minus 12n squared, 3n. Oh, it's not. It's sorry. It's 3n plus. It's 15n in the first bracket. Sorry, minus 15n. So there's no n. Sorry, isn't that right? Yeah. Yeah. Thank you. First prize to whoever spotted that. So it's just 3 over that. Is that positive or negative? How does that compare to 0? Positive. Positive? Yeah? Can you explain why it's positive? I mean, well, I mean, you're right. I mean, such a quantity could be negative if the n could be negative. But of course, the n is the index of this sequence, so the n is a positive integer. So 3 is positive, and these two brackets are certainly positive, because n is positive. So it's just 3, something positive, divided by the product of two positive things. So it's certainly greater than 0 for all n bigger than or equal to 1. Okay? Because all factors are positive. You multiply together a lot of things that are positive, you just get another positive number. Okay, that's good. We've examined the difference, and we've successfully compared it to 0. And there's no humming and hawing here about it does something funny at the front of the sequence and then something different for the rest of the sequence. This applies across the whole sequence for all n is bigger than 1. So i.e., so it's this difference bigger than 0, but that's the same as saying Sn plus 1 is bigger than Sn for all n bigger than or equal to 1. So it is indeed, indeed we've found the same conclusion here. It's an increasing sequence. Term Sn plus 1 is always bigger than the one that came before it. So it is an increasing sequence as expected. Is that okay? Any discussion on that? Any clarification or yes, question?
Since the denominator is squared, n squared,
Yeah.
could you just solve that and see if it's greater than or equal to 0 to see if it's decreasing or increasing?
Yeah. So what are you saying that if you look at the quadratic in the denominator, it's going to be something which is all above the x-axis? Yeah, yeah. So that the denominator, yeah. So is that true about that? Because it could also be something like this, that it could go negative sometimes. But no, but it's for all parts of it are positive, aren't they? Or no, but I don't know. Yeah, because it is this picture, isn't it? Because there are two. It's -5 over -5 quarters and 1 quarter, isn't it? It's got those two roots. Yeah. But you're correct. Yeah. So like you can argue that once you get beyond n equals 1, it's going to be a positive. Well, but that's kind of more or less the approach I was taking here. But yeah. Because the danger is if it was a quadratic that did this, well then, so there might be some parts of the sequence for which it was going negative. Yeah, that's a good observation. Any other questions?
Was it minus?
Sorry?
Was it minus?
Was it?
Minus.
Probably. Did I say plus a quarter? I was writing. Yeah, but I did put it on the negative side. So half a point there for spotting an error. Yeah, you're right. That's good. Okay. Why don't you take a moment to have a go at that sequence F there? Do it together with your neighbors. Have a discussion about it. I'll give myself a break from speaking, and then we'll look at, see what we think. N squared over 2 to the n. So you can choose between doing the ratio approach or the difference approach to that, of course. So hands up who's trying the difference approach on that one. Hands up who's doing the ratio. Well, 50-50 split. You got any conclusions? Is this increasing or decreasing? Or do you want a few more minutes? A few more minutes. So is it increasing or decreasing? I see someone nodding their head, which is the correct answer. It is increasing or decreasing. Do you want to go for one or the other? No? Sorry? Decreasing. Who said? Who's there? Decreasing. Good. All of it, all the time, or?
Not all the time, but some of the time.
Most of the time. That's the right answer. Yeah. So when I did the graph of it. So most of the time is right. So it increases for a little bit at the beginning, maybe the second term, but then it's decreasing. And it's converging to 0. Yeah. I mean, we can kind of appreciate that here. I mean, it's n squared over 2 to the power n. And for a large value of n, okay, when you take a large n and you square it, it gets quite big. But when you do 2 to the power of a large number, you're multiplying 2 by itself a very large number of times. That grows really, really fast, exponentially fast. What we call exponential growth. 2 to the power of something. 2 to the power of the parameter, where the parameter is increasing, then that's exponential growth. And 2 to the power n quickly becomes gigantic. So yeah, it kind of looks like it's going to be decreasing. When you look at it at the initial part of the sequence, yeah, it's very clearly decreasing. So hopefully we could persuade ourselves of that when we look at this way of looking at it. I think the ratio test kind of falls onto the page slightly easier. So we go fn plus 1 divided by fn. It's got n plus 1 all squared, 2 to the n plus 1. And you're dividing by fn, so you multiply by fn flipped, the reciprocal. The 2's cancel, so just leave a half. So all the 2's here cancel with those, just leaves 1 behind. And we got n plus 1 squared over n squared. So you can think of that as n plus 1 over n, all of it squared. Or another way, as that is 1 plus 1 over n, all squared. Now this is the ratio approach, so we're going to want to compare this to 1, of course. Now, how do you compare this to 1? Well, it's a half times something. So if you want to compare that to 1, really it comes down to what how this bracket compares to 2, whether it's bigger than or less than 2. Because then you're going to half it, and that will tell you whether it's bigger than or less than 1. But recall the square. Let's recall the square root of 2 is approximately, or begins, what is it, 1.14 or something, I think? 1.14 something? What's 1.41. You sure? Yeah. Oh, so it's 1.14. Anyway, yes, of course. Yeah, so certainly for n strictly bigger than 2, 1 plus 1 over n is going to be strictly less than 1.41, isn't it? For n equals 2, it's 1.5, but then for every n bigger than 2, it's going to be less than that. So this thing is going to be strictly less than a half times 2. That's something less than the square root of 2, so when you square it, it's going to be less than 2. So this is going to be less than 1. But we've got this condition for n strictly bigger than 2. So that's why at the beginning it just increases. The 2 bits, yeah, the first element is there just on the y-axis itself. Between 0.5. Sorry. So i.e., for n strictly bigger than 2, we've got fn plus 1 is strictly less than fn. Okay. So if the fraction is less than 1, that means fn plus 1 is less than fn. So yeah, so it's a decreasing sequence. Decreasing sequence after n equals 3. From n equals 3 on, it's a decreasing sequence.